talking about powertrain optimization using electrohydraulic systems. In regards to Adam Fry, he's our design engineering manager for North America at Poclain Hydraulics. He's working at Poclain Hydraulics. He's within the industry, fluid power industry, for more than 13 years now. He has a BSME from Grove City College in Pennsylvania. He works for a long time already with the CCEFP, which is the Fluid Power Association for Development as well, and NFPA. As a collaborator in that, working also with the kids in the Fluid Power Challenge program to continue the education program and trying to get more engineers and kids being interested in being an engineer for fluid power in the future. So with no further ado, Adam Fry presenting the program. Thank you.
Thank you, Marcus. So, as Marcus said, I'm Adam Fry. I am unfortunately not Jean Heren, who was supposed to give this presentation. Jean is our engineering manager for our electromobility division. So I am the fill-in in his stead. So I hail from the hydraulic side, more on the motor side. I would just like to remind that according to the IFPE rules, rotten tomatoes can be thrown. However, frozen tomatoes and rocks are prohibited. Phones may be thrown, but they will not be returned, and they must be either flagship or one previous generation. So please bear with me. Okay, so electromobility is a key topic in our industry right now, and it's something that our company is focusing on. We have recently created an entire electrical mobility division, studying what are the best ways to marry the advantages of hydraulics with the advantages of electrical power, creating drivetrains that satisfy our customers' needs. Today we'll go over some overview. This will be a relatively, not terribly detailed presentation, but giving you some background on what are the drivers for electrification, what are some of the key impacts for off-road machinery. We will look at several architectures. We will focus on one of those architectures in a little bit more depth. We will look in depth at the components that make up an electrohydraulic drivetrain, as well as some of the details of that technology, how to optimize it, and with some questions. Feel free to ask any questions. Feel free to interrupt at any time. There will be a dedicated time at the end. If I'm not able to answer them, I will certainly take down your question, relay it on to John, and we will get you an answer very quickly. What are some of the drivers for electrification? One of the key drivers for electrification is the increased environmental consciousness driven by rising temperatures and the focus on global warming. So this goal is to reduce carbon dioxide emissions in every way possible. And many countries believe that electrification can be a solution in this regard. Regardless of the exact amount of temperature rise or the position on this, the reality is that this is being pushed by both governments and customers, and so we as an industry need to be prepared to adapt to it. Another key driver for electrification are large urban centers such as cities. According to a UN estimation, in the next 30 years, there are expected to be nearly 2.5 billion more people living in cities, and they even estimate a slight decline in rural populations as more people move to the urban areas. This drives a further need for quiet solutions and solutions that can be deployed in an area that has already challenges with pollutant gases, smog. Electrification brings some advantages in those areas. One of the groups that's pushing this is called the C40, which are some of the largest cities in the world. These cities represent 650 million people and almost a quarter of the world's GDP. It's actually now much larger than 40 cities. There's nearly 100 and growing, and these cities represent many of the largest cities in all the countries around the world. Another driver for electrification are autonomous and connected vehicles. The increased usage of sensors and computers, guidance systems lends itself well to a fully electric vehicle or an electro-hydraulic hybrid. Here's one example. This is a small autonomous crop seeding machine. This project was called MARS, which was the Mobil Agricultural Robotic Swarm. So this was a system of many small robots, scalable from a small farm to a large farm, all working together. The advantage for an end user is that if a machine is unavailable or damaged, they can swap it out and put another one in instead, scale as their farm grows. As we mentioned, noise reduction is a key factor, especially in cities. No one wants to wake up with the sound of a diesel engine outside their window anymore. Another area that might not be completely obvious at first is total operating costs in conditions in places like underground in a mine. Gases really not tolerated. Let's put a tax on a ventilation system. Transitioning to an electro-hydraulic system reduces the strain on those ventilation systems and allows the mine to operate more effectively. So over the last 5 years, batteries have tremendously improved their performance and their price. So 5 years ago, we really felt that this was a field that was still in the future, still had some large challenges and something that we saw on the horizon. Today, we really believe that within the next 2 to 3 years, it may be cheaper to build an electric vehicle than a diesel vehicle. And a lot of this is being pushed by the electric vehicles also coming out of China. Here we see a graph. On the left, we see a graph of cost per kilowatt hour. And we see that the actual results have been reduced by almost half in only the last few years, with projections to further reduce that cost by another half. And it's actually interesting that so far, this technology appears to actually be better than the roadmaps that have been established for it. At the same time, the power density is increasing per size, which allows for easier integration into a vehicle and really optimizing the system based on the customer's needs. Some of this is driven by different battery technologies, such as lithium iron phosphate, which has no rare earth metals. There's also been increases in energy density in things like lithium polymer. There are challenges and trade-offs with the different battery technologies, and fortunately, we're not going to go any deeper in that because I really don't know any more information on that. But some of the costs and challenges to consider are how quickly can you recharge it? How quickly can you pull the energy out of it? And is it a safer battery technology or not? How unstable is it? So some of the drivers that are pushing this are obviously the reduction of rare earth metals wherever possible, increased economies of scale as more and more electric vehicles are on the streets, as well as just general industrial improvement. So there's also likely going to be further improvements in the future as more solid state batteries are deployed. However, this is still something that is in the future. They would be probably smaller, but allow faster recharging. So today, it's completely acceptable to stop every couple of 100 miles and fill up a vehicle with a fossil fuel. However, no one wants to stop for 2 hours and recharge their battery. If that time could be reduced to 5 or 10 minutes, the consumer acceptance is much, much higher. We have actually seen some OEMs move to fully electric vehicles, and they are able to do this, they claim, for an equivalent performance and an equivalent or potentially even better cost than the diesel machines that they were making. But we see that there are really some strong pushes behind this technology, and we believe that really within the next few years, it will go from being something that we see on a couple stands, a couple prototypes, a few machines, to really truly being an alternative and competitive technology for traditional fluid power. Okay, looking at what are some of the impacts for off-road machinery. So we have seen in the last few years that as emissions requirements continue to get tighter and tighter, that ties up more engineering resources, that ties up validation cycles, and that really feels like redesigning something that already works. That puts a lot of constraints into a vehicle with after exhaust treatments and diesel exhaust fluid, things that really take up a lot of space and potentially are very challenging to integrate. So companies are now being pushed to develop true zero emission vehicles. Again, this is a focus for particularly urban areas, places with emissions or regulation requirements. But of course, it must be done in a way that satisfies the end user. The end user is not willing to compromise performance or cost to have this. So it needs to be cost effective. Looking at several machine architectures, we have a traditional hydraulic drivetrain. We have a fuel tank, a diesel engine, a pump, and then a hydraulic wheel motor or axle transferring that torque to the ground. There are several alternative architectures that exist. For instance, an electrohydraulic drivetrain, where the internal combustion engine is replaced by a battery and an inverter, driving an electric motor, driving a pump, still maintaining the hydraulic wheel motors. Another option is a full electric drivetrain with a battery, inverter, straight to electric motors, straight to the axle. Now this has some disadvantages that we will look at briefly. There's also combinations such as a hybrid electric drivetrain with a fuel tank and diesel engine. However, that would be driving a generator, and that would be driving the electric motors on the ground. Today in this presentation, we will only be focusing on the first architecture, the electrohydraulic architecture with the battery, inverter, and hydraulic wheel motors. So what are some of the drivers in the choice of architecture? Obviously, there are conditions. What are the environmental conditions of the machine? What is the duty cycle? How hard is it used? What are the power requirements and the weight geometry? And then especially the mission profile. And you may ask, what is the difference between a duty cycle and a mission profile? And that's really a key question, and that's something that we'll look at in just a slide. So an electric vehicle brings constraints that we may not be used to working with when we're talking about a combustion engine. Obviously, the performance of a battery at -40 to +40 is not going to be necessarily consistent or the same as expected. How are components protected? What kind of environmental contaminants are we faced with? Are there any specific standards and regulations that must be complied with? What about the machine architecture? How is it used in the day? Not just how hard is it used, but what is the operator doing with the machine? If we look at two different use cases, we have on the top a machine that works for 5 hours. It recharges for 2 hours, potentially over lunchtime, works for a final hour at the end of the day, and then is essentially plugged in at night. On the bottom, we see a machine that works more intermittently, works for 2 hours, is charged for an hour, works for 2 hours, etc. And we see that in both cases, there's 6 hours of work and 2 hours of charging, but the implications for the machine architecture and dimensioning are very, very different, and we'll cover that in just a moment. What kind of charging facilities are available? Can the machine charge while it's doing another operation? Is there a fast charge operation nearby? Looking at duty cycles, all of the power requirements of the machine need to be considered at the same time. Not just a traction for a drivetrain, but the implements, the steering, the tools, what is the maximum, the peak power requirements, as well as the average power requirements. And just like any good design, better data in, Ideally, good data acquisition on an existing machine will equal better machine geometry coming out. So this is an example for a gradability scale between two machines. I know it's a little hard to see, but there's a green curve and a red curve. How do two machine geometries compare to each other? Well, WinGPS is our proprietary tool, but really any machine dimensioning tool that you can imagine would fit that role. How do architectures compare to each other? What's the max pressure and flow? Also considering things like steering. Weight distribution and geometry is a key factor in all machine design, but now we have a large battery pack to deal with. Are we able to take that battery pack and put it in a more optimum position? Are we able to spread it out throughout the machine? Are we able to build the machine geometry around it or incorporate it even into the chassis somehow? What can we do with that in order to potentially positively affect our center of gravity and our performance or avoid negative impacts? So, first step for designing a vehicle is collecting the input data. Obviously, the best case is to use a data acquisition on some form of existing machine or a mule to get as close as possible. Really sitting down with the customer and evaluating what is the mission profile, how does the machine work, what are the different edge cases that we really need to consider that could lead to a very dissatisfied customer, and then what changes, what is open to changing on the integration. All of that is obviously the input data. Once we have that input data, we roll into a pre-sizing phase where we estimate what would be some potentially advantageous architectures based on our existing knowledge of components and machines that might be similar, and size them as close as we think is appropriate. Taking those pre-sizing models and selecting the best, then we enter into an optimization loop where we really get down into the detailed calculations, maybe with very sophisticated tools at a granular level to understand the impacts of each choice that we've made, potentially further weeding out the worst of the architectures and only keeping the best. There are many models out there for each of those components. Potentially the best solution is to combine them all into one sort of analytical model and evaluate the total system performance and not just component by component, as may have been done in the past. Control strategies need to be considered. This optimization phase may obviously drive a loop back, but hopefully at the end we come out of it with a machine geometry that really matches what the customer's expectations are for durability, cost, performance, machine autonomy, and range. It's okay. At this point, we can see an architecture of a machine. This would be potentially like a small articulated loader where the internal combustion engine has been replaced by a battery pack. There's also command modules driving an electric motor right here, driving the pump. So what we see is we still maintain a hydraulic pump. However, that hydraulic pump is driving traditional hydraulic wheel motors. Now, one of the advantages of this for the customer is that they're able to preserve existing geometry, which may already be qualified. It already has a reputation for excellent durability. It's already been exposed to the field elements, and any issues have been worked out. So it can be more of an incremental step for a customer. They don't need to tackle an entire machine redesign at the same time. They can preserve existing elements that are known and proven. Okay, so schematically, this is what it looks like. Each machine will have a large battery pack. This battery pack is typically controlled by something called a BMS, or a battery management system. There will be an inverter controlled by a set of electronics, potentially with a display in the cabin. At the same time, we will still need to preserve for redundancy, safety, and startup a traditional 12-volt battery to run things like lights, supervision of the battery management system, make sure that there are fail-safes that are always active. And once that power supply and delivery is complete, we see an electric motor driving a pump driving the wheel motors. Now, one advantage of an architecture like this is we limit the amount of change. Today, pumps and motors are relatively known commodities. Everyone has worked with them in the past. We have an idea of how much they could cost. Things like an electric motor are very much an unknown. We don't really have a should cost value for this. By preserving a traditional hydraulic drivetrain at the ground, we're able to limit that uncertainty to only one component, rather than multiplying it by 4 wheels. So on the machine, we can see some changes that we don't have emissions. We don't have a tailpipe. We don't have a fuel tank underneath, so we may be able to increase our ground clearance. Okay, now we will dig a little bit deeper into an electrohydraulic drivetrain example. So hydrostatic drive converts engine power to tractive force and speed as determined by the user. Typically, this is a closed-loop circuit. A hydraulic motor allows to operate in all 4 quadrants. It operates as a motor moving forward, as a pump while still moving forward, or as a motor and pump in reverse. However, we're not always able to take advantage of this characteristic because the internal combustion engine has a limited engine retarding facility, especially due to the downsizing of the engines. We cannot absorb all that power. So we're often limited into primarily a propel forward and sometimes a smaller hydrostatic braking. However, one of the advantages of electric motors is that they do not share these same limitations. So an electric motor allows full 4-quadrant operation. This facilitates things like regenerative braking and energy storage during all operations of the machine. So now we can take advantage of the full motor displacement during a braking cycle and recover that energy back into the battery. And as we'll see in just a second, that can be critical because, again, we come back to that mission profile. What is that machine really doing? Because the more we can save out of regeneration, the less we have to recharge it, and the smaller we can dimension our battery pack. Okay, so let's first review the technologies used on the electrical side. So, again, a large battery with a battery management system, an inverter, and then the electric motor. When we think about energy storage, 1 liter of gasoline, about 1 liter diesel, both of them approximately 9 to 10 kilowatt hours. So, depending on the size of the tank, somewhere between 200 and 600 kilowatt hours available for use. However, a lithium-ion battery for the same energy can be potentially 50 times larger, which is an enormous increase. So we obviously have to upsize as much as we can within the constraints of the machine geometry, but also do everything possible to reduce the required energy to complete the job. Again, when can we recharge? When can we recover energy? So different technologies exist for motors. We have inductive motors, we have permanent magnet motors, each with varying levels, each with trade-offs. Some of them have trade-offs on efficiency or cost or performance. And we'll see that sometimes we need to make sure that we're considering this within the framework of the entire system, because the key is reducing the battery pack. It may be much more significant to be able to operate with a smaller battery pack, which may save us much more cost in the long run. So this presentation, we will continue with the permanent magnet motor. even if the cost can be one of the negatives. So looking at an inverter efficiency map, we see that we have speed and power. Typically at higher speeds, we have higher efficiencies, but at lower power requirements. That's the optimum position for the inverter. The motor operates relatively similarly. So our global efficiency map, we want to stay at a relatively low power requirement and relatively high speed. So now the advantage of a radial piston motor, and here we see a cross-section of a traditional hydraulic motor made up of several modules, a bearing support which carries the ground loads into the chassis, a rotating group comprised of a sinusoidal cam ring, a rotating cylinder block with pistons, and then a fluid distribution module. Efficiency curves for a typical motor look like this. So we see that the motor operates better at a relatively moderate speed, but rather higher pressure. Typical motor has a very high volumetric efficiency and a relatively consistent mechanical efficiency. So when we look at our circuit, we see that we have a variable displacement pump. The advantage of this allows us, in conjunction with the electric motor, to tailor the ground speed to operate in an efficient domain. Another advantage of hydraulic motors is that we can deactivate some of the lobes of the cam, put them into a bypass mode in order to reduce the required flow at a speed. And this is all done in order to find what is the right combination to give the best efficiency on an entire machine level. Okay, so if we look at optimizing the drivetrain, here's an example where we looked at earlier, where we had 5 hours of work time, 2 hours of recharging, and then 1 final hour of work time. If we dimension this application with a 3 kilowatt charger, we see that we need to have a 40 kilowatt hour battery pack. We want to keep about a 15% capacity for reserve on the battery so that we don't completely discharge it. However, this is a very large battery pack and very expensive. When we compare that to the second architecture, where we have intermittent charging throughout the day, if we can also increase the charger to a fast charger, a 9 kilowatt charger, we are able to reduce the required battery pack down to only a 25 kilowatt hour battery pack, which is a tremendous cost savings. So this is an example where focusing on the few percentage points efficiency on one or another component will not bring the same level of gains as really truly understanding the mission profile and trying to reduce the battery pack and potentially several hundred kilograms off the weight of the machine. So again, we're able to reduce weight, decrease size, and improve cost. Obviously, this has to be counterbalanced with what is our ability to recharge that battery. Other options include things like the Eco Drive concept, which is on the left we see the typical efficiency map for an internal combustion engine, which wants to operates more effectively at a moderate speed and a higher power, versus the electric drive motor, which wants to operate at a higher speed and a lower power. Because the hydroelectric concept utilizes a variable displacement pump, we are able to tailor the flow while still operating in the preferred efficiency quadrants for the electric drivetrain. Increasing speed, decreasing power. This allows us to have greater range on the vehicle, reduced heat generation, and obviously downsizing is always an advantage. However, now we have to make sure that we have a good control algorithm, the right electronics on the machine, and it requires a variable displacement pump. Energy recovery can be another area where we can leverage the 4-quadrant design of the hydraulic portion of the electrohydraulic drivetrain. For instance, the swing function on an excavator or hydrostatic braking would be forms of kinetic energy that we're recovering. We may also be able to recover potential energy. For instance, our company is a French company, so they always find a way to put a grape harvester making wine into every presentation. But a lot of these slopes are very steep. So as the machine rolls down the hill at a constant speed, that's potential energy that we can recover. And it makes wine. So looking at a 2-dimensional schematic, this is an AIM-Sim schematic of the drivetrain for a loader propel operation. In orange, we have the auxiliary functions, and in blue, we have the traction functions. So we can see that they're not all active simultaneously. There are phases where the machine is stopped and the auxiliaries are working. We also have phases where we have tractive effort is required and still demands for energy from the auxiliaries. We will note that the auxiliaries never go negative on this example. However, we do have periods in the negative region for the drivetrain where we would be able to recover energy. So there we can see that. Another option that we have in order to optimize the drivetrain is looking at multiple pumps. Taking our previous example where we have phases where only the auxiliaries are working, perhaps the main pump that we had sized previously is not appropriate for driving these. Potentially the flow is much lower, or there are different operating conditions or pressures that are required. So in this case, maybe we can add a second pump, potentially a smaller pump, to only utilize that pump when we're required to. Again, looking at overall system efficiency rather than component by component. So in this example, simulating with 2 pumps allows us to increase the autonomy of the vehicle from 110 minutes to 150 minutes, which is a 33% increase. Okay, so what are our levers? We can optimize energy storage, how we charge the vehicle, how we use the vehicle. We can optimize our control algorithms to make sure that the overall system is operating at peak efficiency. We can optimize our energy recovery options, hydrostatic braking, downhill operation, boom lowering, and we can optimize the actual machine geometry itself with multiple pumps.